Hey, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey guys, we're going to talk about Ohm's law and resistivity. Resistivity, that's a word. It's not resistance. That's not equal to resistance, but they're related. So we talked about earlier or in a previous video, we learned that the resistance of something depends on various things, right? If I have a wire, it's to some degree, not to some degree, it's totally dependent on how long the wire is. Because as the electrons, I'll make the electrons red, as the electrons are traveling through the wire, okay, they're going to be bumping into objects. I'm trying to, and as he hits, it's going to slow him down because as you apply a force through an electric field, let's say the electric field is in this direction, so that's going from positive over here to negative charges over here. As it moves, it accelerates because you're applying a force, and force is mass times acceleration, which we've learned, in the past, right? And so the further it has to travel, the more things it bumps into. So the length of the wire makes a difference in terms of the resistivity. But also, if I were to have a thicker wire, right, if the wire was thicker, all right, maybe the wire should be blue. If the wire was thicker and as the electrons are traveling through it, they're going to have more space if it's thicker. And lastly, the thing that sometimes you don't think about, it also is what material it's made out of. If you recall the last video, tie-dye guy, he passed electricity through clay. That's a much more resistive environment than, say, a copper wire. All that said, there is just an equation. So resistivity, or the resistance of a wire, or of anything, not just a wire, it could be Play-Doh, it doesn't matter, is equal to something called rho, that's the Greek letter rho, times L over A. Now, this P right here, the rho, it's the Greek letter rho, R-H-O. There's tables of rhos, and if you look over here, I've got one of those tables. So the resistivity is, now notice the units are in ohms meters. For copper, it's 10 to the minus 8th, 1.7. Aluminum, 2.7 times 10 to the minus 8th. That's why copper is better than aluminum for wiring. Tungsten, 5.6 times 10 to the minus 8th. You get the idea. You want something with the lower the resistivity, the rho, if you will, the better of a conductor is. Muscle, it's 13. That's a big, big number. Fat's even a bigger number for it to pass through, et cetera, et cetera. And pure water, that's huge. You get the idea. That's why you don't want to put things into water, electricity. So, and then what's L? L is the length of the wire. And A is the surface area, the cross-sectional surface area. So if I have a wire, right, a wire is actually a circle, right? And so the cross-sectional would be pi r squared. You also have some wires, if you will, that are rectangles, right? You might see this question on a problem where you've got, for example, in the back of your car, there's this line that is your defroster. And that is actually a square wire that they embed into the glass, and then they pass electricity through it, and then they can determine, and then they heats it up if you live in a cold climate, which we don't in Houston. But if you did, you could turn that on, and it will defrost like there's ice on it. It'll actually melt the ice when I used to live up in Chicago. So the big idea here that you're going to need, if you will, help on is this is the key equation right here. The resistance, that's just the resistance measured in ohms, is equal to this rho. Rho is these terms right here, times the length divided by A. And as you might be recalling, this is our equations, electricity equations. Here's that equation listed right here. And then we've got this table and then the equations we've gotten used to using in class. Hey, Houston, we've got no problem. We'll see you in class.